Lecture for module 2.1. We are looking at chapters 1.6 through 1.11. And we've already done 1.12 in the previous video, so I'm not going to be going over that in this lecture. We're going to be stopping with molecular orbital theory this morning. Before we get started, let's go ahead and start off with a word of prayer. Dear Heavenly Father, Lord, thank you for today. Thank you for all the blessings that you have given us. I ask that you please now give me the words to say so that the information can be clear and those watching this video can understand it. Also, anyone who's watching this video, if they have a prayer request on their hearts, Lord, I ask that you please just answer it according to your glory. In Jesus' name I pray, amen. All right, you guys. So let's not waste time. Let's go ahead and get started. We're going to first start talking about the hybridization. And let me do this so that you guys can see the screen clearly. And let's go. All right, so sp3 hybridization is, let's see if I can do this though. There we go. sp3 orbitals and the structure. So we're going to talk about hybridization. Now, hybridization is a result of bonds. When they are formed, they create a hybrid orbitals, okay? So when you have bonds that are formed, when you have atoms that come together, you have a hybrid orbital. And that hybrid orbital is based off the notion that once they form, the electrons are spread out through the whole atom, the whole molecule, creating a whole new type of orbital when they're being shared between those, okay? And so first we're going to talk about sp3. All right, so we talked about how carbons are tetrahedrons, right? They're tetravalent, they're tetrahedrons. And so they create this shape that you're seeing here, this geometric shape that you're seeing here, okay? So this geometric shape is a result of it being bonded to 4 independent things, okay? And so what you have is a overlap, okay? So these hydrogens have the 1s orbitals. And then this carbon here is demonstrating an sp3 orbitals, a hybrid sp3 orbitals. And so these bonds here overlap of the 1s orbital and the sp3 orbital. And let's see. The best way to describe this, or kind of how to say this, is pretty much when you're bonded to 4 different things, you have the sp3, okay? Now, the bond angles, or excuse me, the bond length, let's talk about the bond length first. The bond length of the carbon to the hydrogen. And so from here to here, you see a bond length of 109 picometers. Now, this is important along with the 109.5 bond angle, because this bond length, this bond angle is what gives the attributes for tetrahedrons. And so when you're looking at when something is bonded to 4 different things, as you see here, in 4 different regions to give it sp3. When you're looking at other atoms and how when they're bonded to 4 things, if they have those same bond length and bond angles, then we can know that they're classified as that same sp3, which would have similar attributes, okay? And again, the bond angle is when you have this, you see this angle right here that's been creating by the hydrogen and carbon. Right here, you have, that's the bond angle, okay? All right, so 2 carbons bond to each other by an overlap of an sp3 orbital from each, okay? So before we're looking at methane, now we're looking at ethane. And so here, you now have an sp3 orbital from this carbon that is bonding to the sp3 orbital of this carbon. So while these right here are still the 1s to sp3, this bond here, okay, It's sp3 to sp3 overlapping. Because remember, the bonds coming from the carbon are sp3 because that's that tetrahedron shape, okay? So 3 sp3 orbitals on each carbon overlap with the hydrogen 1s orbitals, all right? And so if we're looking at the bond strength from the carbon-hydrogen bond in ethane, you see that's 421 kilojoules per mole. Okay, so that's very strong bond. And that means these carbon-hydrogen bonds are not going to really be broken easily. All right. And then with the carbon-carbon, you see that the bond length is a little bit different. All right, it's a little bit longer, it's a little bit further away. Okay, with those two sp3 orbitals overlapping. And the strength is slightly weaker, okay, but it's still strong. Now, as far as the bond angles, those are still the 109.5. So you still see the same bond angle that you would expect to see with the tetrahedral, okay? However, the bond length and the bond strength is going to be different. And that's due to the size of your nucleus and how many shells or how large the orbitals are of the two carbons. All right, so let's look at this and actually seeing these orbitals, okay? So again, this carbon has 4 sp3 regions, okay? So you have your 1, 2, 3, 4. The same thing you see with this carbon. And so when they come together here, you have 2 sp3 orbitals overlapping. And this creates what we call a sigma bond, okay? So these bonds are overlapping this way, all right? So they're kind of going like this. That's going to be a sigma bond. All right, so when you have that sigma bond, you have that sigma bond. Here you're seeing, while this is a tetrahedral, I know I said 109, and it's still close in that region. However, you're seeing here that it can be observed to be a little bit higher. Okay, so now let us do a work problem. All right, it says draw a line bond structure for propane. All right, propane. Now we haven't talked about naming hydrocarbons yet. We'll talk about that a little bit later. But this right here is the condensed structure. So you're going to take this condensed structure, you're going to try to draw this. Now this is a line bond structure. So this is going to actually show your carbon and your hydrogen bonds, all the individual carbon-hydrogen bonds. Okay, and then after that, we're going to predict the value of each bond angle and indicate the overlap shape of the molecule. So let's go ahead and put the structure up. Okay, if you guys want to just pause the video to try to do it yourselves, you can do that. If not, we're going to just keep on going, and I'm going to show you an example problem. All right, so this is how you draw the bond structure of propane. So if here you see the CH3, so the carbon with 3 hydrogens around it, that's from here. Then you have a carbon that's in the middle of 2 carbons right here. And that carbon has 2 hydrogens attached to it. So you have your 2 hydrogens here. And then at the bottom, as you see, there is a carbon here with hydrogens. You see your CH3, which is the same as you have here. Okay. So that is your line bond structure. So now let's answer the second half. So this carbon that is here, the carbon that is here, and the carbon that's also here are all bonded to 4 different things. That way we know that that is sp3. And if you could think of it, you have that S1 that's understood, P3, so 1 plus 3 is 4. Yes, I can remember it here, right? And so these are all sp3s. Now these hydrogens that just have that 1s orbital are overlapping it. So if you're looking from the hydrogen to the carbon, these are going to be 1s to sp3 overlapping, whereas these are going to be sp3 to sp3 overlapping. So let's look at this. So because these are all sp3s, it is going to be a tetrahedral geometry. Also, let's go here. All of these bond angles that you see are going to be approximately 109. All right, but again, as we saw, you can have some other things, but if you notice, because of this here, you're still going to have that 109 bond angle, okay? So if an exam has anything, you're looking at tetrahedron and bond angle, they're always going to be approximately 109. All right, so again, you can see all of that. Oops, excuse me. All right, so next, let's talk about sp2 orbitals. We just finished talking about sp3. Now we're going to talk about sp2. Now, sp2 orbitals are derived by combination of an s orbital, an s atomic orbital, with two p atomic orbitals, okay? So if you look at our structure here, you have two, okay? You have two p orbitals, all right? And you have an s atomic orbital. So sp2 orbitals are in a plane with an angle of 120 from each other, and the remaining p orbital is perpendicular at the same time. So we're looking at the structure here going, this is kind of looking at it straight on. And then the other angle is if you're looking at it from the top view. So as you can see, you have your p orbital here, which is the top of this p orbital. And then you have your sp2 orbitals going around it in the plane, okay? So two sp2 or hybridized orbitals overlap to form a sigma bond. All right, so the sp2 orbitals overlap, because remember they're going this way, so this is going to create a sigma bond. Whereas the p orbitals that are perpendicular, when those overlap, they create a pi bond. So when you have bonds overlapping like this, which are sp2 orbitals here, that's sigma still. But when the bonds are overlapping like this, they have the pi bonds. And the electrons are going to act differently because of that, which you're going to see later on as we continue to study more complex molecules. So sp2 and sp2 sigma bonds and 2p pi bonds result in a sharing of 4 electrons and the formation of a carbon-carbon double bond. So whenever you see those carbon-carbon double bonds, one bond is the overlapping of sp2 orbitals. The other bond is a pi bond, which is an overlapping of the p orbitals. So the electrons in the sigma bond are centered between the nuclei, and the electrons in the pi bond are occupy the region on either side of the line between the nuclei. So we're going to see what that looks like. All right, so this right here is an sp2 orbital. And we're seeing it next to another carbon with an sp2 orbital. And so these right here, these electrons, as you see, are centered between the nuclei. So this is the nuclei of the atom. And these electrons are centered in between that. So you're getting that sigma bond with those electrons being centered. Whereas the electrons that are in the bonding orbitals, all right, they're on either sides, all right? So the double bond in ethylene is shorter and stronger than the single bond in ethane. All right, so this right here is going to be kind of pulled closer. Okay, it's pulled closer. So it's a shorter length and it's stronger. And you can see the bond angles of this part here is going to be at about 120, okay? 120, and you see that with all the bond angles are about 120. Now do notice that the bond length of carbon hydrogen is still about the same 109, but you can see that there's a difference in the bond length of the carbon where it's gotten shorter. All right, so now it says draw the electron dot and line bond structures of formaldehyde. Now I need to show you guys what that structure looks like because I'm sure you don't know what formaldehyde looks like. But we're gonna draw it out and then we're going to talk about it. So we're looking at an electron dot and line structure. So this right here is our electron dot, all right, also your Lewis structure here. And you can see that you have the two electrons being shared between the carbon. Now, if I need to, I can do an extensive explanation of how to draw Lewis dot structures, or I may just post that up just for a review. You should be able to do that from more general chemistry. However, I know it may be rusty over the summer, and so I will post. It may not be my lecturing, but someone that I think is really good, I can post up a lecture for self-help of the Lewis dot structures and how to draw them. All right, so with these Lewis dot structures here, you can see that for the each of these atoms, they are fully shared based on giving the octet. So the hydrogens, again, they can only form two because they're in that 1s orbital. So you have the two electrons, so that hydrogen is nice and happy, and stable for both of those. This carbon has it's still tetrahedron because you have that one. We can look at here, you can see it better. You have that 1, 2, 3, 4 bonds around that carbon, and the electrons being shared amongst that are a total of 8. You can see the 8 electrons. You have 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 being shared around that whole thing, but yet you still have that tetrahedral so that you have those 4 bonds. And then the oxygen is also happy because oxygen has a valence electrons of 4. So you still see 1, 2, of 6, Oxygen has a valence electrons of 6. And so you can see there that you have 1, 2, 3, 4, 5, 6. And so that is happy, but yet all the electrons that are being shared with that oxygen is a total of 8. So it's following that octet rule while still satisfying that stability of the valence electrons that it is able to contribute. Now, let's talk about the orbitals of what's happening here. So this carbon is connected to 3 things. Because it's connected to 3 things, we call those, the orbitals is going to be the sp2 orbitals. And so you have the 3 sp2 orbitals here. You have 1, 2, 3, and then you have your p orbital that is the pi electron here. And so the carbon-hydrogen bond is 1s to sp2, 1s to sp2, and then here you have sp2 orbitals interacting. Now let's see if I can see it here. The oxygen also has 3 domains, and so that's also an sp2 overlapping orbitals there. All right, so carbons can also form, so now we're moving to sp. So carbons can also form triple bonds, all right? And so with triple bonds, you're connected to 2 domains, and so you have an sp orbital, hybridized orbital, okay? And so the carbons, when you have a triple bond, that's a total of 6 electrons that are being shared between 2 atoms, okay? Now, with carbon, 2s orbitals hybridized with a single p orbital giving 2 sp hybrid orbital. So 2p orbitals remain unchanged. So I'm going to show you guys what that looks like, okay? So here what you have is you have your sp hybridized orbital, which is here. So only one right there. And so you have your two lobes there. And then your p orbitals here, you have two sets of them. So you have an sp, and then you have two sets of p orbitals that remain unchanged. So when they're overlapping, again, the sp orbitals are going to bond to create a sigma bond, which is in between the two nuclei again. Whereas the p orbital electrons here and here, when they overlap, they're going to create pi bonds. So you have two pi bonds and one sigma bond when you're dealing with a triple bond. This again. So again, the line in the middle can signify the sigma bond, and then the two lines on the outside can signify the two separate pi bonds. Now, this is the shortest and the strongest carbon-carbon bond. So if you can see that it's linear, so it creates a 180-degree angle. If you notice also, the bond length is shortened. So it was 154 before, now it's 120. Now the carbon-hydrogen bond length is still close to 109, but it does slightly shorten because of the electrons kind of pulling the protons in a little bit closer there. So here goes an overview of everything that we talked about in terms of the bond strengths and the bond lengths. And as you can see, again, that with their carbon hydrogens, which is here, 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 and here, they're relatively all about 109. However, you can see a significant change, a relatively significant change with the bond lengths of the carbon-carbons. So it starts off at 154, and then it goes to about 134, and then lastly 120. And you can see the bond strength also increases as you increase multiple bonds. All right, so now let's draw a line bond structure for propyne. Propyne. Again, you hear that prop, that represents 3 carbons, prop. And again, we haven't talked about naming, but when you hear that, remember propane, okay, that prop represents 3 carbons, and the ane, the ene, and the ine represent how many bonds you have, and we'll talk about that more. But right now, let's focus on just drawing this. So go ahead and try to draw this. If you want to take time to try to do it yourselves, go ahead and pause the video. If not, go ahead and keep watching. I'm going to show you as an example. Predict a value for each bond angle. All right, so let's look at this. So we're going to draw it out. So we have the carbon with 3 hydrogens on it right here. Then that carbon is attached to another carbon. Now this carbon doesn't have any hydrogens on it, as you can see here. But then this carbon is triple bonded to this carbon here, and it has 1 hydrogen at the end. And we notice that all of our carbons have 4 bonds around them. So let's check them. So carbon, we have 1, 2, 3, 4. So that's good. This carbon in the middle only has 1, 2, 3, 4. So that carbon's good. This carbon here has 1, 2, 3, 4. So all these carbons are drawn correctly and orderly. Now let's look at the bond length, or excuse me, let's look at actually the hybridization of each of these. So this carbon is connected to how many different things? It's connected to a hydrogen, another hydrogen, another hydrogen, and then a carbon. It's connected to 4 things. Therefore, that's tetrahedral. So the orbitals there would be sp, 3 orbitals around that carbon. So when it has the hydrogen attached to it, that's a 1s to an sp3. So each of those carbons, hydrogen bonds are sp3 to 1s or 1s to sp3 bonds. Now, the carbon to carbon bond, since this is sp3, but this one right here is bonded to how many different things? It's bonded to a carbon and another carbon. So it's only bonded to 2 things. So that's going to be sp. Okay? sp. So the bond between the carbon, 2 carbon bonds here and here would be an sp3 to an sp bond overlapping. And then here you have the carbon here, which is bonded to also 2 things. So that's sp again. So you have an sp to sp overlapping bonds. And then lastly, you have a 1s to sp that we already established overlapping with the carbon hydrogen bonds here. So let's look at this again. So you have sp3, sp, and sp, and all of these hydrogens again are 1s's. So let's look at the summary of all of that. So carbon 3, so this right here was our sp3 orbital, and it's bonded to the 3 s orbitals of hydrogen, as well as overlapping with the sp here. So overlaps sp orbitals of carbon, and then one within 1s orbital. So that is the other carbon on the other side that has a hydrogen attached to it. And then this is the one inside of the middle here with the sigma bond, and then you have your sp3 to sp orbitals, okay? So you have your carbon 3, which was the sp3, your carbon 1, which was the sp on the end, and then your carbon 2, 3 bond, which gives you that. All right. Cool. And then, of course, we have 3 bonds there, sp1 to sp2. And oh, the 3 bonds there, let's not forget, let me go back. Let's not forget that when these overlap here, this right here is a sigma bond in the middle, but then you're overlapping it with 2 pi electrons, 2 pi bonds, excuse me, there. Giving you a total of 3 bonds. All right, so these are the bond angles. So when you have your tetrahedron, that's 109, but then when you have your sp bond, that's going to be 108. All right, so here are some hybridizations of some other atoms other than carbons. And so we're going to kind of look at those briefly. So with nitrogen, it still gives you that tetrahedron shape because of the lone pairs that are possessed there. And so you still see a bond angle of about 109. Again, when you're dealing with oxygen here, it still has 4 domain areas, 2 bonded and 2 pairs of non-bonded electron pairs, but it's still 1, 2, 3, 4. So you're still having that sp3. All right, and again, you still see that attributes of about 109 degrees. So next again, with phosphorus, even though there's a double bond here, that phosphorus is still bonded to how many different things? 4. So you have sp3 again. And you see again that you still see that about 109 bond angle. It says 110 to 112, which is still kind of goes and implies that it's sp3 hybridized. And so again, you're looking at how many, not how many bonds you have, but how many different things it is connected to, including your lone pairs. So again, we have sulfur. Now, sulfur is slightly different than the other ones that we looked at. While it's still described as approximately a sp3 hybridized, if you notice, even though it's bonded to 4 different things, you see your bond angle is significantly smaller at 96.5 when you're looking at these here, or 99 here, okay? And it's because these electrons are a little further apart, pushing that bond angle in just a little bit more. All right, so let's talk about identifying all non-bonding lone pairs of electrons, because we really need to talk about this, especially when we're talking about the oxidation numbers. And so let's go ahead and start identifying the non-bonding lone pairs. So we're looking at dimethyl ether, which is here, which is an oxygen with 2 CH3s on both sides of it. Again, we're going to talk about the naming, but this right here is called dimethyl ether. So what geometry is expected? Well, you can pause and you can try to fill in the lone pairs and kind of think about what oxygen electrons will be around the oxygen, or you can just keep on showing and watching me. All right, so here you have oxygen. And we know that oxygen is going to have a total of 6 valence electrons. And so because of that, whenever you have oxygen bonded to 2 different things, you have 2 sets of lone pairs. And so because of that, this will be sp3, this will be sp3, and this will be sp3. These will all be sp3. So you're still going to have that tetrahedral geometry for this molecule, okay? the oxygen is still going to have that tetrahedral, and that's because of the lone pairs that we saw even in the examples previous to that. All right, so we're going to shift to the last 1.11. And this is the description of covalent bond formation as a result from a mathematical combination of atomic orbitals to form molecular orbitals. So what does that mean? That means that when covalent bonds are forming, you have your atomic orbitals, which is what we talked about before. But when they combined, they create molecular orbitals. And those molecular orbitals, what we were observing and talking about before, are because we've seen that the electrons are forming, in a sense, its own nucleus, which is because they're spread around the whole molecule, not just individual atoms. So it's a better description of what's happening when bonds are formed. So with molecular orbitals, today we're going to talk about bonding molecular orbitals and anti-bonding molecular orbitals. So bonding molecular orbitals are molecular orbitals that is lower in energy than the atomic orbitals, which is formed. So you have your atomic orbitals, but when they form, the bonding molecular orbital is the orbital that has lower energy. And so in this world, things want to be able to conserve energy. So when the bonds are formed, it has a lower energy orbital. The anti-bonding orbital is the orbital that has a higher energy than the atomic orbitals by themselves, okay? So let's visualize this. So let's look at hydrogen. So you have two 1s orbitals here. These are your atomic orbitals. When they form, they create bonding orbitals, molecular orbitals. That's a sigma bonding molecular orbital. And if you notice, if energy is being increased, this bonding molecular orbital is a lower energy than when they are by themselves. And then here, the anti-bonding orbital that has the nodes there. So that means the signs are different, okay? They have different energy levels, and so, energy signs. And so because of that, you have this anti-bonding molecular orbital, which is unfilled. So this is not filled. So the two electrons that these hydrogens brought to the plate are going to fill in the bonding molecular orbital. Even when you're dealing with p orbitals. So let's say you have two p orbitals, all right? So when they're combined, the molecular orbital is filled, and you see how they're combined, they're filled. However, the anti-bonding creates a node, and with these, the orbital is not filled. So only the bonding molecular orbital is occupied. And the pi anti-bonding molecular orbital is from combining lobes with opposite sides again, okay? So this is, you see how the signs are opposite? All right. Whereas here, the signs are the same. And so you see these orbitals that do not have a node. All right. And so that is actually the end. So let's do a quick summary. So organic chemistry is simply the study of compounds that are carbon containing, carbon backbones. You notice that all our molecules have carbons in the backbones. That's what the study of organic chemistry is about. Let's see. Atoms are charged nucleus containing positive charged protons and neutrally charged neutrons. And then around that, the atoms have electrons that are negatively charged. Now, these electrons that are negatively charged is what gives the properties to the atoms, which causes them to desire to be bonded to each other because they're striving to be perfect, that octet rule. So electronic structure of an atom is described by a wave equation, and the different orbitals have different energy levels and different shapes, okay? The s orbitals are spherical and the p orbitals are dumbbell shaped. So remember, you see that all the s orbitals are spheres, and then versus the dumbbell shapes. All right. Covalent bonds are electron pairs that are shared between atoms, okay? And then the valence bond theories are the electrons that are being shared around in the outermost shell. And again, those are the ones that are doing the reacting, okay? Or those valence electrons. So valence electrons are important to be able to identify and be able to measure based on using the periodic table. Molecular orbital theory, which is the last thing we just talked about, or well, we just talked about that, but we have one more thing to talk about after this one. It's bonds that result from the combination of atomic orbitals to give molecular orbitals, which belong to the entire molecule. Okay, so again, you have atomic orbitals. When atoms are bonded, you have a molecular orbital, and that's an orbital that represents for the whole molecule. And then last, we're getting close to the end. We have the sigma bonds, we have the pi bonds. We know that sigma bonds are orbitals that are overlapping like this, whereas pi bonds are overlapping based on the perpendicular p orbitals. Okay. Carbons use hybrid orbitals to form bonds in organic molecules. In single bonds with tetrahedron geometry, carbon has 4 sp3 orbitals. In double bonds, planar geometry, carbon uses 3 equivalent sp2 hybridized orbitals and 1 unhybridized p orbital. So you have 3 sp2s and 1 p orbital. All right, and notice it's always 4. So 4 sp3, 3 sp2s, and 1 p orbital. Still a total of 4 because it's tetrahedron. Carbon uses 2 equivalent sp hybridized orbitals to form a triple bond with linear geometry with 2 unhybridized p orbitals. So again, you have 2 sp hybridized and then 2 p orbitals. A total still of 4 orbitals. With carbons, you're always going to have a total of 4 orbitals. Okay, whether it's 4 sp3s, whether it's 3 sp2s and 1 p orbital, or 2 sps and 2 p orbitals. It's always a total of 4 orbitals because, again, carbons are tetrahedrons. So atoms such as nitrogen, oxygen hybridize to form strong oriented bonds, and you're still able to observe that sp3 hybridize. Nitrogen atoms in ammonia and oxygen atoms in water are sp3 hybridized. And we did see with sulfur, even though slightly different, it still has sp3 hybridized characteristics in a little. All right, structures in which carbon-carbon and carbon-hydrogen bonds aren't shown are called condensed structures. So now we're going to 1.12. So if you guys remember, the carbon-carbon, carbon-hydrogen bonds, when you're not showing all the bonds and sticking it out, that is your condensed structures. And let's talk about the other ones. So you have your cupola, which is when they're stretched out, and then you have your electron bond structures, and then you have your line structures as well, where you're not showing your carbon hydrogens, which we did a little bit in this chapter. And we're going to do more of that in chapter 2. And so, yes, I hope this lecture was beneficial to you. And don't forget to write a comment of how you feel about it. If you write comments or extra things, even can ask a question inside of your quiz. You can do that. That way I can respond and answer those, whether in our office hours or direct messaging to you through the quiz, all right, through the feedback. So again, I will see you guys in the next lecture, or you'll see me. Bye.